Extraction VX. John Whitson, CS6968, Final Project, Summer 2014. VoIP data extraction, the fundamental problem. Network anonymizers and signaling encryption can hide the IP addresses and VoIP signaling information for people who are trying to monitor traffic. So how do you correlate these calls together? Well, it's a manual process, and the approach we've taken is to study background noise for the similarity across the calls, and in the understanding that similar background noise can imply the same caller, or at least a caller in a recognizable noise environment. And some obvious noise include obviously music, which we would call periodic background noise, or electrical equipment, which is narrowband continuous noise. So the goal was to provide a first-pass tool to aid an analyst in making this kind of a decision or a correlation as to whether different phone call sessions from the audio could be from the same party or the same person. Without this kind of a tool, you would have to sit there and listen to the entire phone session, which takes a lot more time than the solution we actually have come up with. The key technology here is Fourier signal analysis in the frequency domain, also known as a spectrogram. And it is an image that shows across the top axis the frequency in hertz of the frequencies that you were looking at, from 0, which is what we call DC or direct current, all the way up to the maximum number. In our case, it's about 4,000 hertz and 256 samples. The vertical axis is going downwards, and that is time, because we take the signal from the audio up and chop it up into pieces using Fourier analysis so that we can see the transition of frequencies as they go forward in time, and that's looking downward. Okay. You can identify narrowband noise information, such as patterns like this where you see a streak in the vertical. You can also see wideband information, is when you see consistent patterns out over here. In this case, it's quiet, and also it shows the patterns of the speaker's voice. So there's obviously been a lot of research in trying to identify speakers from their audio patterns, and so that is why there's so much energy here. The brighter the pixels, the more energy there is in that frequency range at that time. And the gray is a grayscale, which is then topped out by yellows on top of that. And the very absolute peaks are shown in a red scale, so you'll see red scattered around. To do this, we actually analyze the spectrogram both visually, but we also provide a set of routines called feature functions that look at the spectrogram itself and try to find interesting effects in it. And those are typically frequency peaks, the ones that have the most energy in them, and long-term noise and other noise patterns. The development on this project, in quick summary, the objectives we kind of discussed already. As a necessary activity was to construct a data collection environment. Obviously, it would be nice if we had some audio sessions to work with, and the one from the Natroba file really wasn't much to work with. So we had to obtain some voice phone software, some VoIP SIP service providing services, and do some multiple captures. And unfortunately, Wireshark, which had been in our original plan, does not correctly extract the audio data to a file, so we had to go do it manually. But that's just as well, because that wasn't all that difficult. We then also have to code and process multiple internet protocols to support this. Those are the Session Initiation Protocol, or SIP, the Session Description Protocol, or SDP, and the Real-Time Transport Protocol, RTP. And on top of that, we also have to decode the actual sample data using ITU G.711 mu-law pulse-coded modulation companding, which is a form of compression in the energy of the signal, not a true data compression. After we understand all that, then we can write Python. So the coding aspect of this actually followed an awful lot of research. And the discussion on VoIP extraction and the Wireshark experience, I refer you to the VoIP module that I uploaded or had given to the Sci4 project. So the result is fundamentally two Python programs, VxScan SIP, which basically finds and extracts the audio from the PCAP files and the supporting metadata, and then VxCompAudio, which takes that extracted audio and builds the spectrograms and does some feature identification and puts it out in an easy to read format. It has dependencies on a couple key packages, namely the dpacket package, the numpy package, or numerical Python, and the Python image library, SQLite3, those typical things. When you do the dpacket, please note you must get both dpacket through pip and dpacket fix. There is a bug in the UDP code for the standard dpacket distribution, and you must get the fix. Otherwise, dpacket will not properly decode the UDP data and it'll throw an exception. Future work in this area, obviously we had such time limits and scope limits because it's a project in a class. This kind of technology is similar to what's used with sonar in submarines for acoustic analysis, and entire people and organizations make careers and PhDs out of this kind of work. So we were able to get some feature functions and the structure in there, but if people really wanted to get interested, they should add more feature functions. We also totally blew off encryption impacts. There is encryption that's possible, but we have not looked at any of that for reasons of scope. We also limited ourselves to UDP protocol packets only. SIP and SDB can be TCP. RTP really doesn't work well with TCP because if it hangs up waiting for an acknowledgement, that's a big problem, as we'll talk about later. With the audio data that we have at 8,000 bits per second and 160 bytes per UDP packet allowed, that is 50 UDP packets per second being processed. And if TCP has to hang up with an acknowledgement on that, that's a problem. We also really would like to go beyond the G.711 simplest audio coder decoder, also known as a codec. This is one of the oldest ones around. It's at least 20 years old, but it's free. And there are CD quality audio ones with encryptions, one with better compression and compounding. But again, that's all future work. What do you need to execute this? You need to have a PCAP file with some VoIP sessions in it. You need to know the local IP address and net mask for the PCAP file. That's a function of VoIP. VoIP sessions actually talk from a client, the local one, to a server, a remote server, so that we need to know the idea of local in order to keep track of who's talking to who. We also need to know the server control port number. Okay, this is important because they are usually proprietarily assigned. So the one we had was 5060, that's for getonsip.com. But you can look at Wireshark at the PCAP file and do a filter on SIP, and you will see which ones contain the control signals, so then you can pick the right port number. There are 4 steps, 2 programs with 4 steps. The first one essentially is to initialize the database file as clean. Different from the other projects we've done. In this case, the database is persistent, which means that once we create the database externally, we can run the programs that update the database over and over again on mixed files, and it will put new content in the database and retain it. The database is not cleared every time you run the program. So you need to use VX initDB in order to create the database and the schema for that file. You then run VXScanSip on your PCAP file with the basic information it's looking for. You then run the analyzer, vcompaudio.py, on the audio files that it generates. And you can actually run that on audio files in the same format, which is just the raw MULA encoded samples that were not run most recently by ScanSip. It won't have any of the networking information, but it will have the rest of the information in there. And then run Firefox on the result, and that shows you the HTML. We chose HTML this time for the project because we wanted to integrate imagery in the visualization product. And whereas my normal preference for this kind of data is Excel, it is hard to embed an image in Excel. So in terms of the details, we talked about that the database is persistent. We used HTML in order to do this. The code was actually designed in such a way as to add new feature functions easily. All the feature functions are defined in vxfeaturefuncs.py by themselves, and you just have to add their reference into a configuration function at the bottom, which we'll show you later. And then the code in Compaudio automatically imports the vxFeatureFuncs module, calls the configuration function, puts it in a list of functions to call for each audio session that it wants to analyze. So in this way, it's extensible without having to rewrite the system. There are two other utilities included. Run baseline and is one of the shell scripts, how to run some of the basic data with the supplied PCAP files. The other one is VXplay audio, which if you have SOCKS installed in order to play the audio through your system, you can run that script and it will actually play back the audio with all the appropriate switches and parameters, and you can hear the individual sessions as a real person. This is just a very quick example of the script that is used. This actually is run test, which is on one of the other files that we have. It's on the cap3 PCAP file. So first we have to initialize the database. We then run the scansip with all the correct parameters for the local network, and then we run the comp audio, and finally we run Firefox. Okay, this concludes the overview part. The next part coming up will be a short code walkthrough, so please look for the files for that. Thank you very much.